In the last video, we saw that phi implies psi was logically equivalent to a well-formed formula that didn't use the connective implies, and I mentioned that that meant that any well-formed formula at all was logically equivalent to one which didn't use implies, so which only used not, and, or. That property of not and or is called adequacy, and it's what we're going to explore in this video. So here's the definition. A set of connectives is called adequate if every well-formed formula is logically equivalent to one using only the connectives from that set. So let's recap what we saw last time. We saw that if you have phi implies psi like this, that is logically equivalent to psi or the negation of phi like this. And this means that you can express, if you have any well-formed formula, it's logically equivalent to one which doesn't use implies, because any time you have an implies symbol, you can use this logical equivalence to get rid of it. For example, if you had something like, let's choose an example with a lot of implies in it. So P implies Q implies R, then using the equivalence that I've just written down, that's equivalent to, I think I'm going to be a bit lazy and miss out some brackets. So this is equivalent to Q and not P implies R. That's just using this this equivalence that we wrote down above, and then of course that's equivalent to R or not Q or not P. So it might not be a very attractive, well-formed formula. It might look a bit complicated, but we can use this method to express, to find, given any well-formed formula at all, a logically equivalent well-formed formula that doesn't use implies. So that was the point of this. What we've got here has no implies in it. So what this shows is that the set of connectives that's just or and not is adequate. In fact, there are even smaller adequate sets. So we're going to give a sketch proof that actually just or and not together are adequate. So why is this? So proof, we know already that the set of connectives or and not is adequate. So every well-formed formula is logically equivalent to one only using or and implies. So all I want to do is get rid of the and from this. So how can I get rid of the and? Well, we can use De Morgan's laws. So De Morgan's laws tell us for any well-formed formulas phi and psi that phi and psi negated is logically equivalent to negation of phi or negation of psi. Okay, so what happens if we negate both sides? Then if we negate both sides of this, we'd have a double negation on the left. So if I take phi and psi on its own like this, again I'm going to miss out some brackets just for readability's sake, that's equivalent to double negation of phi and psi by the double negation rule, and that's equivalent to the negation of phi or the negation of psi. So this is just by using the logical equivalence right here. Then we have a way of expressing and in terms of not and or. So what you'll notice here is that there is no and symbol. So using this repeatedly, using this logical equivalence, we can find a well-formed formula. Let's say this slightly differently. So given any well-formed formula using or and not, we can find a logically equivalent well-formed formula that only uses or and not. Okay, so this set with just 2 connectives in it is adequate. And you might ask, can I do better? Right? Is maybe just 1 connective on its own adequate? Well, the answer to that is, using the connectives we've met so far, no. So none of the connectives and or not implies are adequate on their own. That's an interesting thing to think about as to why that's true, or how we might prove such a thing. But I promise you that it's true. So none of the 4 connectives, the 4 main connectives that we deal with, are adequate on their own. But there are single connectives which are adequate. So if we define a connective called down arrow, or sometimes pierce arrow, to have the truth table which I've drawn just here, then this connective on its own is adequate. So every well-formed formula is logically equivalent to a well-formed formula that only uses the connective down arrow. So if you look carefully at this table, you can actually see, you might recognize what this is. So can you spot a logical equivalence between phi down arrow psi and a well-formed formula that uses our main 4 connectives? Pause the video and think about it. Okay, I hope you did that. What you will see, if you think about it for long enough, is that phi down arrow psi is logically equivalent to the negation of phi or psi. Okay, so I'm not going to prove it, but actually this down arrow on its own is adequate. Every well-formed formula is logically equivalent to a well-formed formula that only uses down arrow. Just to get you started in figuring that out for yourself, you might notice that, for example, not phi is logically equivalent to phi down arrow phi. Okay, well, why should we care about this one element adequate set? Why would that be interesting? Well, on the right of the picture there, you have the Apollo guidance computer and the user interface to the Apollo guidance computer. The gold bit is the actual computer. That is the thing which did the navigational calculations during the first manned mission to the moon in 1969. And as a computer, a digital computer, it has to do a lot of logical operations. And the computer, in order to do logical operations, uses what are called logic gates. So logic gates are electronic devices which behave like logical connectives do. Now, because NOR on its own, that's the name for this down arrow connective. So let's write that down actually. So, oops, what do we call this? We call this, oh, come on. We call this thing NOR. Because NOR on its own is adequate, they could do any logical operation that they needed to do, the people who designed this computer, only using NOR gates. And it was actually advantageous to them to do this, to only use one kind of gate in the computer. And so the Apollo guidance computer, which went to the moon in 1969, contained around 6,000 NOR gates.